All right, thank you for that introduction. For those who don't know me, I am James Festa. I'm a grad student at UCLA working with Dr. Jochen Stutz. Today I'm going to talk to you about BRO observations we took during the 2013 NOMADSS campaign using a limb scanning DOAS device. So BRO is a very important atmospheric constituent due to its participation in the catalytic destruction of ozone in the stratosphere and troposphere. It's also important because it converts gaseous elemental mercury, or mercury zero, into reactive mercury. And as you can see from the second figure on this slide, excuse me, BRO concentrations are anti-correlated to the concentrations of ozone as well as mercury zero. Now, free tropospheric BRO concentrations generally range between 0 to 2 ppt. Some studies do suggest a ubiquitous background, possibly in excess of a ppt, whereas other studies propose a more varying concentration. So during the NOMADSS campaign, our group operated an aircraft limb scanning max DOAS system, which we called the mini DOAS instrument. Now, the instrument consisted mainly of 3 telescopes mounted to the exterior of a C-130 aircraft. Each of these telescopes recorded the backscattered radiation in the UV, visible, and near-infrared regions of the solar spectrum. Now, the data I'm going to show you here today, however, is solely in the ultraviolet, however. And as I did mention, this is a limb scanning device, so these telescopes were mounted to motors so we could scan above the aircraft, below the aircraft, as well as ahead of the aircraft, when conditions warranted, of course. Now, DOAS, or the differential optical absorption spectroscopy technique, is best described using the Lambert-Beers law. Basically, this describes that as light propagates through the atmosphere, it undergoes extinction through scattering events and absorption events. Now, the DOAS analysis relies heavily on our ability to separate broadband spectral structures from narrowband spectral structures, and we do this by fitting a polynomial function on the measurement spectra, as this indicates, or this is associated with atmospheric scattering events. We then fit trace gas cross-section references to the remaining spectra, and these fits are related to the slant column density of that trace gas, which are the number of molecules within our optical path length. Now, the data I'm going to show you in the beginning of this talk, however, are in a differential slant column density format. And these are pretty much the same thing as slant column densities, although we do subtract slant column density of a solar reference. Now, if you're familiar with the DOAS analysis of BRO, our analysis procedure followed very similar to what was described in Aliwell et al. 2002. We did slightly change the spectral fit range, however, in addition to using a third-order polynomial to describe those broadband spectral structures. Now, throughout the NOMADSS campaign, we really didn't see BRO significantly above our detection limit, with one very notable exception. And this took place during Research Flight 6 on June 19, 2013. At this time, we were over central Texas, ascending to an altitude of around 7 kilometers when we intercepted this high bromine air mass. And as you can see from the first figure on the slide, this shows our DSCD analysis from this flight. The first part of the figure shows our ascent up to that altitude of 7 kilometers, where we notice a very strong increase in our BRO DSCD signal. When we level off at 7 kilometers, however, we detect a DSCD of roughly 7 times 10 to the 13 plus or minus 1.4 times 10 to the 13 molecules per centimeter squared. Now, ultimately, our ultimate goal is to derive BRO mixing ratios. And we do that by running a radiative transfer model for 2 really important reasons. The first, we don't know the optical path length ahead of the aircraft. This depends on atmospheric composition as well as the aircraft altitude. We also don't know the sensitivity from our instrument above the aircraft and below the aircraft, even though we're only looking in the limb. Now, in order to understand that sensitivity, we do have to run the radiative transfer model and have differential box air mass factors calculated. Now, this is the figure I'm showing on this slide. These differential box air mass factors are the sensitivity function based on altitude for our instrument. And this specific image here, or figure, took place during this portion of high bromine content that we found in this atmosphere. And as you can see, is what you would expect. At 7 kilometers, we see the most sensitivity ahead of the aircraft, which is straight ahead of the aircraft. However, there is some sensitivity arising from above and below the aircraft through multi-scattering occurrences and the Earth's curvature effects. And because of this, we do need to take that into account of our analysis. We run the radiative transfer model so that we can simulate the differential slant column densities we see in the atmosphere using our spectral analysis from what's outputted in our radiative transfer model. Now, once these two differential box air mass factors, once these two slant column densities compare between the radiative transfer model and our spectral analysis, the concentration at flight altitude in our RTM for the input BRO profile will be that of our concentration in our actual atmosphere as well. Now, we use the McArtim radiative transfer model, which is a Monte Carlo model, and this was developed in the University of Heidelberg in Germany. We tried to constrain it as best as possible with in situ measurements whenever available to better simulate the radiative transfer of our atmosphere, in Science Flight 6 rather. Now, we did this by computing, or producing temperature pressure profiles, in situ gas profiles taken from the ascent immediately prior to reaching this 7-kilometer altitude. We did have to take a few of these inputs, however, from literature as they were not measured during the campaign. These values include the aerosol refractive index, gas cross-section values, as well as our initial BRO profile that we used. And once again, once we run the radiative transfer model, the outputs are differential slant column densities as well as those differential box air mass factors or the sensitivity functions. Since we did take a few of these values from literature, we did have to run sensitivity tests to determine the overall uncertainty of our radiative transfer calculations. And as you can see from the table on this slide, none of our sensitivity tests really changed the overall output of our differential slant column densities significantly, which tells us one very important thing. The vast majority of our uncertainty does come from our spectral analysis itself. Now, I'll draw your attention, however, to just one fact on here, and that when we increase the amount of BRO in the troposphere, or which is technically just below the aircraft in this case, we only saw a change of around 0.5%, indicating that we are somewhat sensitive to other altitudes, however, not near as sensitive to the atmosphere ahead of the aircraft. We also performed an O4 comparison for the DSCDs between the RTM as well as our spectral analysis. Now, O4 is a collisional complex between the oxygen molecule, and this is very important for us because oxygen is well mixed in the atmosphere, and it's also well quantified. We know, the concentration. So if we can produce a proper comparison, this tells us that both analyses are observing the same optical path length as each other, and which is extremely important, of course, for determining BRO concentrations. Now, with this comparison, you can see it actually turned out quite nicely. We did most of our they compared within 10% of each other on the vast majority of cases, indicating that our radiative transfer model calculations were well constrained, and we were properly taking atmospheric scattering and absorption processes into account. Now, running the radiative transfer model, we did determine a BRO mixing ratio of 1.9 plus or minus 0.35 ppt at the 7-kilometer altitude. Now, this is a substantial amount of BRO, but the 0.35 indicates our 1 sigma uncertainty limit, or uncertainty. And because of that, we ran the RTM with this as an upper and lower limit, as you can see in the simulations on the first figure of the slide. And all measurements taken within this air mass are well described by these simulations, as you can see. I also have plotted here the initial profiles we used in our RTM analysis for BRO, of course. And as you can see, as we were ascending to this altitude of near 7 kilometers, we encountered a very strong increase in BRO, which could also be seen by the increase of our DSCDs, as I had mentioned previously. Not only did we see strong increases of BRO in this air mass, we also saw very strong decreases in ozone concentrations, as well as relative humidity values. Relative humidity fell to around 4% in this air mass, signifying that it was a very desiccated air mass, and originally led us to believe that the source of this bromine could possibly be stratospheric in origin. However, the low ozone contradicted this hypothesis, of course, where values were observed around 32 ppb at their lowest value, so anomalously low for 7 kilometers altitude. So in order to determine the source, we did run a 315-hour back trajectory using the high split model, and this is around 13 days. And you can see the origin of the air mass is likely over the equatorial Pacific Ocean. At 13 days prior to this, we also were monitoring satellite imagery from 13 days prior to this origin site. It noted a very strong convective system located within the ITCZ in the immediate vicinity of this origin site. Knowing that the marine boundary layer is a region that contains high bromine content as well as low ozone, we do propose that a convective system, possibly this one or another, lifted this marine boundary layer air into the free troposphere, whereas horizontal transport brought this to the North Pacific high, allowing the air to descend to warmer layers, lowering that relative humidity to what we sampled over Texas. And further transport, of course, brought this to Texas over our sampling site. Now, we also ran a feasibility test to determine if this amount of BRO could persist for 13 days in the free troposphere. We did this by running an RCAD 8.2 chemical 1D model, but I want to stress that we ran this as a box model by setting vertical exchange coefficients to just about 0. And we noted that after 13 days in the free troposphere in this model, 1.9 ppt is in fact a feasible early afternoon value that we could observe. I also want to draw your attention to the fact that, and you'll probably notice that inorganic bromine concentrations did increase during our model time. And this is just because of the breakdown of organic bromine species, particularly that of bromoform. And this does contribute to an inorganic bromine source throughout the model run. We did iterate the initial model chemical inputs so that the model outputs would better match the measurements taken on the aircraft, which you can see in the table on the slide as well. I do want to mention that we were required to initially put a substantial amount of NOx into this air mass, anomalously above what you would expect in the marine boundary layer. And this is because, well, to better match the aircraft measurements, of course. But this may offer even more validation to the fact that this air was convectively influenced because lightning is a known source of NOx. Let's see here. So just a brief summary and conclusions. We did find an air mass that contained 1.9 ppt or plus or minus 0.35 ppt of BRO in the free troposphere. We were able to, we propose that this bromine originally came from the marine boundary layer and was convectively lifted into the free troposphere. And we ran a chemical model to confirm that this amount of bromine is in fact feasible in the free troposphere for a mid-afternoon value. Now, I also want to show you that we ran the chemical model with and without bromine chemistry at all, just to determine the overall effect on ozone, because bromine, of course, significantly affects ozone chemistry. Before I jump into the results, you will see that both simulations, however, show an increase of ozone throughout the model run. And this is simply because of the enhanced NOx we used in the initial part of this model. But with the inclusion of bromine chemistry, substantially less ozone was generated over this time period, indicating the obvious that bromine is, of course, very important to include in tropospheric ozone modeling. Now, I want to close on the idea that this type of convective system or idea might be more important of a source for free tropospheric bromine than previously thought. And it would be interesting for future studies to measure convective outflow over the Pacific Ocean or any convection over the ocean to determine the global scale of such a phenomenon. I just want to thank everybody here for listening to me today. Thank you very much.
Are there any questions?
Yes.
So, some of that event, you said that BRO was below your detection limit?
Yes, correct.
What would that detection limit be?
It varied substantially from flight to flight, mainly because we were, we had this campaign was plagued by cloudy conditions for us, and that, of course, limits how far we can see in the atmosphere, or our instrument can see. So typically our detection limits range from being our best around about 0.6 or 0.7 ppt, which we see in this air mass, up to about maybe 1.5 ppt in a worst case scenario. We did see about our detection limit over the marine boundary layer, but that was the only other situation we did see any BRO in the atmosphere. Oh, sure.
You saw one event during the whole campaign. What makes you conclude that this event may become complex?
That's a very good question. I really don't have a great answer for you, I guess, for that, but man, that is a very good question.